Hi. You all must have frequently heard about these terms relay logic, PLC or MPC logic. What are all this? So this is exactly what we intend to learn in this video, short video. What we'll do is we'll take the example of the starting of a induction motor. So we'll understand the basic fundamental principles using a relay logic, and we can gradually upgrade it to MPC and PLC. We'll add more functions, more logic, so that you will understand by the end of the video, you'll understand the necessity of having PLCs and MPCs. What are the advantage of a PLC or a MPC as compared to a simple relay logic, which was what was used for the last so many years. You are watching Chief Engineer's Tea Time Talk. I am Ramesh and I will be the pilot who will take you to this channel. Hope you enjoy this video. Let's get started right away. The purpose of this video is to achieve the following objectives: to lay the base for understanding controls at a very basic level using relays, and slowly elevate one to understand controls based on multi-purpose cards and PLCs. Immediate objective here is to start the three-phase electric motor and control it with all safety and the logical protection devices. You can see that the motor is connected to a three-phase supply. Since this is a module dealing with topics at a very conceptual level, for the sake of simplicity, I take the liberty of showing a single line instead of all three phases. Obviously, to connect and disconnect this motor from the MSB, we need a circuit breaker. So here it is. Next, for the sake of protection, we need to add a fuse. So this is for people who are nostalgic about the past. But let's just add it, though there may be many modern devices which may make the necessity of a fuse redundant. Next, we need a whole lot of protection devices. Let's include maximum possible for the sake of clarity for the young students, irrespective of the fact whether each and every one of it is actually included in every motor circuit or not. It may be useful for guys who are going for exams to get aware of the possibilities. These include overload, overcurrent, short circuit, ground fault, phase loss and imbalance, under voltage, over voltage, over temperature, reverse phase, possible vibration, speed protection, etc. etc. So many possibilities of imagining what type of protecting parameters could be there for protecting a motor. Now these devices may have individual sensing elements or share some common current transformer and some devices. These devices may operate a single tripping coil. To keep things simple, I am not showing all these in detail. Again, you should remember that the scope of this video is only to deal with the concepts of controls. Hence the wiring diagram, etc. have been simplified and may not exactly reflect the actual logical version as found in manuals. Anyway, the next thing on our agenda is to make arrangements for these controls, which include the protecting devices stated about to work. So we have to have a step-down transformer to be able to supply low voltage supply for control circuit. The red and green being two phases, phase voltage being say 220 volt. Now we add a main contactor coil. Let us call it K1. Now please don't ask me why it is K1. It is because everybody calls it K1 and I don't mind it. This main coil K1 will operate the main contactor, which will actually connect and disconnect the motor depending upon whether current is flowing through the coil or not. So here we go. Now to start and stop this motor, we need to supply this main contactor coil with operating current, which needs to be controlled with stop and start buttons. So here we have a start button. Please remember that this is generally a spring loaded button and you can see it here. So you can also see that it is normally open. Let us also include the stop button. Well, firstly we have no choice, and secondly you will see that without the stop button we cannot manage to energize the coil K1. So here comes the stop button. This is also spring loaded, but you can see that it is normally closed. Now I can see that as soon as we press the start button, current is able to flow to the coil and the contactor K1 is closing and the motor starts. Wow, great. But wait, this start button is spring loaded. So as soon as we release our finger, the start button jumps up, the circuit, the connection is broken. This will result in the K1 coil getting de-energized. So the main contactor K1 will open up and the motor will stop. So unfortunately our happiness was short-lived. Unless you want to stand whole day or weeks pressing that button, which is not possible. So what is the way out? Well, we need to make a small arrangement to keep the K1 coil energized even after you remove the finger. So we add another contact called the holding contact. This holding contact is also operated by the same coil K1. Some people call it auxiliary contact. Now if we operate the start button, K1 is energized and hence contactor K1 and also holding contact is closed. Now if we remove our finger and the start button springs up, disconnecting the connection to open circuit, K1 will still be receiving the current through the holding contact and hence the motor will continue to run. Now next, if we press the stop button, obviously we are breaking the supply of current to the coil K1 and both contactor K1 and the holding contact will be in the open position, the motor will stop. If you have understood this well, congrats. You have understood a concept which many marine engineers previously have struggled to comprehend for various reasons. Now let us concentrate on the protection devices. If any of the protection devices get active, they will energize a tripping coil or tripping relay coil. You can see the tripping coil here, and here is the contact for the tripping coil, which we can call it as tripping contact. You can easily see that if the tripping coil is energized, it will operate the tripping contact and this will open up and interrupt the flow of current to the coil K1, which in turn will stop the motor. Now we have only looked at start and stop of the motor with some protection. We can go on further and add some more logic for the motor to start. For example, here you can see a limit switch. Let me add a coil called A1 and its own contact A1. Here we see that unless the limit switch is in the inactivated condition, the coil A1 will not be energized. That means if the limit switch is still in active condition, the contact A1 cannot be kept closed, which makes sure that K1, the main contactor coil, cannot be energized. We have successfully created a logic which says that unless this limit switch is in the inactivated condition, we cannot start the motor. Going ahead, we add another logic, as you see here. I have added a pressure switch. So I have added another coil A2 and its contact A2. You can now see that unless the pressure switch senses the particular value of pressure, the coil A2 cannot be energized. And it will follow the same logic as we discussed earlier. So finally we have a motor which cannot be started if the limit switch is activated or there is a minimum initial pressure. In other words, the motor can be started only if the limit switch is inactivated and some minimum pressure is there in the circuit. These type of logics and many more form the basis of controls for many of equipment on the ships. But these logics at the moment are based on relays. You can see that the number of conditions and interlocks required for control of a motor are quite limited. The type of inputs are restricted to binary inputs. So a relay based control is quite easy and simple to implement. Now suppose we want to start and control a motor which requires much more complicated logic. Executing the same with the help of relays will become quite a challenge. So we need to move on to the multi-purpose cards. Using a multi-purpose card for the same motor starting, which we are seeing here, we can make something like this. You can see that I have now used a multi-purpose card. The inputs, start button, stop button, limit switch, pressure switch, protecting devices. These all are forming the inputs to the multi-purpose card, and the signal to close the main contactor forms the output from the multi-purpose card. You can see here that if one of the inputs go missing, for example in this case the input from one of the many protecting devices, then the output from the MPC card for closing the contactor is disrupted and the motor stops. the motor cannot be started, or rather we can say it like that. Well, let's pick up only a few of the actual control components and conditions for the sake of simplicity and demonstration as required by a electrohydraulic crane. Actually, they have much more. But the focus of this video is not to understand the principles of a crane, but to understand the shift and necessity or advantages of using controls based on multipurpose cards or PLC. You can see that the type of inputs and outputs are not restricted to binary inputs and outputs. You can see the binary inputs for the operation of limits. You have a safety interlock to ensure that the minimum feed pressure should be present for the crane to work, which is again a binary input. The big cranes are backed up with the encoder driven limit. Now these inputs may be the pulse type of input. The crane operator using the joystick is generating an analog input. The load cell is generating an analog input for decision making. On the output side, we can see the signals are not restricted to binary outputs. We may have binary outputs for operation of contactors for various motors and solenoids. We have pulse width modulation outputs. We call it PWM outputs for control of proportional solenoids for the operation of the crane pumps, variable delivery pumps. We may have analog outputs which may later be modified for display devices. So you see that the complexity has become unmanageable. If these complexities need to be executed with relays, it may make it very expensive, unreliable because of too many physical moving devices. Circuitry will get very complicated, too much of wiring, etc. etc. So here we see that all the inputs are received by the multipurpose card where the logic gets processed, and the outputs also originate from the multipurpose card for control of various output devices. The cards are tailor-made for this particular equipment with the limited capability of inputs and outputs of a particular type as required to operate this particular equipment. So most of the logic is hard-coded with very limited access to operator or programmer. So only a few parameters can be edited, and he cannot load a complete different logic or software. The other option is to use a generic PLC which has extended capabilities. The inputs and outputs can be extended by adding cards as desired. Each card can accept and generate a certain number of signals and certain types of signals. The PLC can be completely reprogrammed to operate any equipment. The control logic can even be completely changed. The same hardware can be used to operate, say today a compressor, or tomorrow a crane, or day after tomorrow a purifier. But the basic difference between the two, in layman's terms, MPCs are cards with limited capability to design to operate a predetermined logic and a particular equipment. PLCs are generic and are capable to be programmed to operate any range of equipment. You can imagine an MPC card is a card inside a video player which can only play videos, whereas a PLC is like a card inside a computer which can not only be used to play a video or play a game or whatever. We can load a software and do some calculations, or you can use it to make documents. Well, this is a very rough explanation for the understanding of a layman. Hope you all enjoyed this video. If you want more such videos, more on the conceptual level, please do message me and put into the comments, and we'll take it forward. Thank you so much for all the patience.